Okay, well, at the end of class last time, we had just demoed the non-deterministic finite state machine. And did you guys get your, able to code up your description of the finite state machine? That was just kind of like our little rote, you know, not too much thought. Good. And what we want to do now, before we go on to the next chapter, let's just take a minute or two right here at the beginning, at the end of chapter 4, 3rd edition, by the way, and see how slick this code is. So here is the figure 4.3 from the 3rd edition, where our author has set up this non-deterministic finite state machine. And we looked at this code last time, what you have to put in your Prolog database in order to implement or to simulate this non-deterministic finite state machine. And notice, so what we have is we have 3 different predicates. We have a final predicate, we have which indicates which states are final states. We have a trans, which is the transition, and the way you read this transition, when you see trans S1A, S1, that means there's a transition from S1 on A to S1. And for the second one, there's a transition from S1 on A to S2, and so on. And then these silent ones corresponded to those empty transitions that are normally denoted by the Greek letter epsilon. So let's take a look at the code. Well, actually, before we look at the code, let's take a look at what does it mean to make a transition. This is so slick. Look. How is it that we can get from the start state S to the final state recursively? And here in figure 4.4a, our author illustrates accepting a string by reading its first symbol or by making a silent move. Because look, what are we saying? What is this, excuse me, what does this figure 4.4a say? It says that we should be able to accept our string, you know, our arbitrary string, if we are in state S and our first symbol is X and it takes us to S1, and then that should succeed if what? That transition should succeed if what? I mean, sorry, the acceptance of the whole thing should succeed if we can go from X to S1 and what? And the transition, yeah, and say that again?
The transition is on the rest of the string leads to the final state.
Yes, starting from S1, the state that we just went to. That's correct. So what it's saying is we can go from S to the final state if we can go from S to S1 on the first symbol X, and then we can go from S1 to the final state. So it's kind of like S1 becomes our new start state. Do you see what I mean? S1 is the new start state for the rest of the string. But on the other hand, we should also be able to do that if we can go from S to S1 on null, and then we can go from S1 to the final state on the whole string, because that means we didn't scan a character. Now look, you guys, that's all you have to do to code up a non-deterministic finite state machine engine. Look, let's go to our demo and scroll through the code. All right, so here's our code. So check it out. How do we, so here are the, so by the way, these rules up here are the ones that implement that, the final and the trans and the silent. These are the ones that implement that non-deterministic finite state machine. And now, what is the engine that actually runs this? How do we accept well, first of all, how do you end this whole thing? If you have what? I mean, how does this, I mean, as we're going through, what are we doing? As we're going through, what are we doing? We're consuming the first yeah, we're consuming all the letters, and then when we get to the end, how do we know that we have, how do we know that we're, you know, how can we accept the empty string? We can only accept the empty string if we're in what kind of a state? A final state. Are you with me? So look, so accepts state with the empty string. So first of all, what's the arity of accepts? 2 is 2, and the first one is of what? A state, and the second one is the list of the characters that were, the list of the symbols that we're scanning. So how is it that the only way this can work, the only way that we can accept it when we're in a certain state, if we only have the empty string left, is if we're in what kind of a state? So therefore, if what? Yes? Final what? Final state. Are we good? So that's how we end, right? That's how we accept the empty string if we're in the final state. But now what? There's 2 ways to make a transition. So, first of all, how can we accept it by reading the first symbol? In other words, when is it? Can anybody anticipate this? How can we accept by reading the first symbol? What should our code be to accept by reading the first symbol? Accepts what? State. Well, but list, don't we need to know? I think we should break the list up into the first and the rest, yeah? Okay. So accept state, X, and rest if what? If there's a transition from what to what? State to some variable, yeah, state on X to some other state, yeah.
Trans, state 1, rest.
No, I mean,
Accepts.
yeah, and accepts, right, and accepts what?
State 1.
Yeah, exactly. Is that amazing? How easy it is? And now how would you accept it by making the silent move? Accepts what? State. And now what? Yeah, in any string. If what? And do accept. Yeah, now we don't make, well, oh, you're right. Yeah, because we're on the same state. Yeah, so if accepts what? Oh, no, no, no. If there's a what? No, no, we have these null. I mean, how do we say up here? How did we say that a silent, there has to be a what? See, because the empty, this is how we note the empty transition. And that's between 2 states. So if what? Okay, silent state, state 1, right? And accepts what? String. Yeah. And that's it. Boom. Now, I mean, can you imagine how hard it would be to code up a simulation of a non-deterministic finite state machine with backtracking in any other programming language? And look how easy it is. That, to me, is just the cat's meow.
And does Will backtrack?
Yeah. Remember, we demoed that last time. Here, look. Check this out. If we do accepts, here, this is one of the ones that we did last time. If we do accepts S1, so we're going to start with S1, and we'll do, remember we did this one, list X1, X2, X3. If we do this will actually go through, and it will find the first one, and then it will backtrack, and it will find the second one. See that? It actually, all that's just, it comes, it kind of like comes out of heaven. You know, it's kind of, it's free. I mean, that's the power of the unification that with the backtracking that's doing all those trials for us. See, searching is really one of the artificial intelligence is a big topic in artificial intelligence, because that's what intelligent people, things, entities do, is they search, they have goals, right? That's one of the things that separates us from animals, is that we have goals. You see what I mean? And so searching, right, you know, we have goal, we have search for a way to get from here to there, and so this is a big, and so the whole searching thing is built into the Prolog engine, and so that's, and it's very powerful. Okay, so that's the end of chapter 4. Let's consult. ch5.pl. Okay, and let's do more on ch5.pl. And now we are going to talk about a very important topic called cuts. Now, so first thing we're going to do is, now you can see here on this top listing of what we just consulted, you can see what we've done here on the very top is we have defined a quadratic function, g of x, y. And what it does is y, now he says function, but it's really not a function. It's a, I mean, maybe I said function. I probably shouldn't have said function. I should have said predicate, because everything is a predicate, right? This is really not, functions return things, but predicates are either true or false. They either succeed or they fail. Okay, so in Prolog. So the definition of this is, the specification of this is y is the square of x. And notice what the way we do it is g of x comma y if y is x star x. So here's how you would use this function. Suppose you want to know what the square of 5 is. Then what would you do? You would say g of, now how would we get the square of 5? How would we do that? Yeah, 5, we'll make it y because that's the second variable, but same thing. Okay? Yeah, so we let our x be unified with, you know, with 5. So x is instantiated to 5, and then and then y is going to unify with y, match with y. Okay? And so it's going to say y equals 25. Now what happens, what do you suppose happens if we do this? G of 25, sorry, g of x 25. What do you suppose is going to happen? Square root, so you think it's going to come back 5? Do you think? Now wait a minute, you guys, what did we learn about is? What does is do? What did we learn about is? It forces what? You're right, it forces something. The computation on what side? It forces the mathematical computation on the right side, and then what does it do? It instantiates the left side to that. But the problem is, how can it do the computation of the right side here? Yeah, how can it, yeah, right. So this is instantiation error. It doesn't know what, it can't do any, you can't do x times x because x doesn't have a value for it to multiply. So now, you see, this is kind of different. Once we get to is, it's different from those variables being instantiated in any order. You see what I mean? Because we're doing arithmetic with is and we're forcing the evaluation. And then what has to be on the left is an uninstantiated variable for it to match to that, to unify with it. Is everybody with me on this? Okay? Now, here's another, before we go on to the next application, here's another demo. What happens if we do 3 is less than 4? We did this before, I think. What happens here? Yeah, and what happens if we do x is less than 4? What happens if we do that? Now can you guess what happens here? Well, but see, it doesn't have those 3, 2, 3, 2, 1, those would all have to be atoms that it can't do that. So what's going to happen here? What does less than expect? Yeah, this is an instantiation. So look, if we instantiate x, if we say x match 2, and then we say x is less than 4. If we do that, then what happens? X equals 2 and what? And it succeeded, right? Do you see what I mean? So now here it can do that. If we do the same thing, but then we say and they say x less than 1, now what will happen? No. Yeah. Does everybody see how? So in dealing with math, it's a little bit different from what we're used to. Okay. So now for our first application, let's go to the slides. Now this next application is an example of a little function that we want to compute, and our author has given us a little scenario here where, see, this is environmentally conscious. He's doing this pollution level. We're trying to monitor the pollution level, right? And so, either the conditions can be, maybe this X represents some sort of a reading on some sort of a pollution meter or some sort of concentration of a pollutant or something like that. And if you're within normal standards, then there is no alert. And then this alert, but if the pollution level gets between 3 and 6, if X is less than 3, then everything is safe. But if X is between 3 and 6, if 3 is less than or equal to X and X is less than 6, then what we want to do is we want to have Y instantiated to alert 1. So that could be like your orange alert. And then if 6 is less than or equal to X, then we say we want to instantiate Y to alert 2, so that could be like your red alert. Red alert, don't go outside, pollution. Yeah? Okay, so so this is the function. Now what we're going to do is we're going to examine this in a lot of detail, and we're going to introduce the concept of a cut using this example. Okay, so let's see how this works. Let's see what our function actually does. Okay, now up here, this in this pane here, figure 5.1, a pollution alert. This is our pollution alert function. Now take a look at how this works. It's kind of like this function here, where the variable is the first argument of the rule, and then we have the possible outcomes to be either normal or alert 1 or alert 2. So the way this is defined is f of x comma normal if x is less than 3, f of x comma alert 1 if 3 is less than or equal to x and x is less than 6, and then f of x comma alert 2 if 6 is less than or equal to x. So that's rule 3. So let's just see how this function works. So what do you suppose happens if I do this? Now you should be able to predict this, right? What happens if we do f 1 comma capital Y? What should happen? Predictions here? Yeah, Y equals normal. And of course, you know what I'm going to do next. Oh, rats. Oh, I didn't. Sorry, I didn't. It was still looking for the next one. Okay, so normal, and I'll just press return. Okay, and then and now what the next one is going to be function. Now instead of 1y, we're going to say 5y. So what happens if I do 5? Obviously. Yeah, y equals. Actually, let's try to see if there's another solution. There is no other solution. Actually, let's do the first one and see if there's another solution. No, there's no other solution. Are you with me? And now let's do one with just the other range there, within the other range. So let's make this 7. So obviously, no mystery here. Oh, but this one, there is no other solution, right? So I didn't have to press a semicolon. Is everybody with me? Now, can you predict this? Suppose we do f of x, comma, 4. Actually, I shouldn't do it. That's a bad, yeah, it'll fail. But suppose I do x, comma, normal. Yeah. Suppose I do x on, yeah, why will this fail? Well, because up here, what's the first thing it's going to do? It's going to try to do x is less than 3. It said this normal will match this normal, right? But the thing of it is, and this x, these two variables will match, but then x is uninstantiated, so this will be the problem. Is everybody with me on this? Mm-hmm. So boom, you know, and it doesn't matter which one we do this with. If we could do it with normal, we could do it with alert 1. Alert 1. But still, it's going to be an instantiation error. Is everybody with me on that? I just need to change my notes here. Okay. So fxy assumes that x is instantiated to a number. All right? So now, how about if we do, do you know what it would be if we did 2? What would happen if we did 2? Right, and is there any other one? No. So what would happen if we did this, and then we ask y match alert 1. So now we want to know if you know, with it, and what's going to happen here, obviously. This obviously, it obviously fails, right? Now this particular query is a very interesting one, and even though we know ahead of time that this is going to fail and it seems kind of trivial, what we're going to do now is we are going to look at a series of slides that I've prepared to show the details of the backtracking with this case. Because, and this will be in preparation for introducing the concept of what's called a cut. All right, so let's go back to our slides and take a look. Okay, so here is this is the definition of, the code that we have in our Prolog database. And this is the one that we know is going to fail, right? But let's take a look at what we want to do is we want to look at exactly how the backtracking works with this particular scenario, this particular query. So look, you guys. So what happens when I typed f2y, comma, y match alert 1? What happened? What's the first thing that Prolog is going to do? What's the first thing what's it going to do? It's going to search for what? What's it going to search for? Yeah, first the F. So it's going to go down, oh, there's an F. And then what's it going to do? 2. And then, but wait a minute, the 2 does what? Yeah, x is instantiated to 2. And then what? And y is what? Instantiated to normal. And then what does it do? It does this, right? And then what happens? Okay, so here, and then what happens? So it goes there, and then what happens? The 2 is less than 3. Are you with me? So then it comes back to here. Now, is everybody clear on that? And then what happens? And then it goes from left to right here, right? And it compares y with what? Alert 1. But what was y instantiated to? Normal. So this one fails. So what does it do? Well, not yet. Yeah, because it doesn't know what's coming up. Are you with me? So what does it do? Now watch this. So what does it do? What do we call it? It backtracks. Now look, this is what's coming up here is going to be crucial. So it backtracks to here, and what happens when it backtracks to here? Now it's this. So now what's happening? Now x is what?
2.
Instantiated to 2, and what? What do we have here? Y is instantiated to alert 1. Does that succeed? I mean, is that true? I mean, that's a match, right? So what does it do? It comes down to here, and it does this. But what did we say x was instantiated to? 2. So what happens here? It fails the first comparison. So what happens? Comes back up here with failure. But then what's it going to do? It's going to backtrack and do this one, yeah? And then what's going to happen? It's going to come to here, right? But now, and x is going to be instantiated to what? But then what's going to happen? That's, wait, no, this fails here, doesn't it? Right? Okay? So here's what happened. Do you remember those tracing diagram that we looked at in the first chapter? This figure 5.2 in our book shows the tracing. It shows that this comes to here, which comes back to here, which comes back to here, which comes to here, which comes to here, which comes to here, which comes to here, and that's when it fails. Now look, you guys, what do you think about that? You are right. It's not efficient. But look, how do you could see from the code that if it failed on that first test, that number comparison test, I mean, once it passed that first, the first time around it passed the first number comparison test, right? But it failed on the what? On the level, you know, the pollution level, right? But you know that once it passed that first one, you know from the logic that it's not going to pass the other ones. So here's what Prolog provides. It provides a way for us to cut for efficiency, because if the programmer knows that you don't have to do this after a certain point, you can put a cut in there and cut all those further trials out. Now, are you with me on that? That's what a cut does. All right? And now what we're going to look at is we're going to look at another version of this. We're going to look at 2 or 3 versions. And this next version we're going to call F2, and this F2 has a cut. And here's how it looks. Okay, so the thing of it is that we know that if x is less than 3 succeeds on the first rule. So here, we know that if x is less than 3 succeeds on the first rule, that it's not gonna succeed here or here. Do you see what I mean? So this second version it's gonna do the same thing, but it's more efficient with this particular query. Now I'm going to get back to the terminology of a green cut versus a red cut, but this happens to be an example of a green cut, and we'll explain that in a minute. But let's take a look at our second version. This is F2, right? So now, what's different between F and F2? There's a comma and a what? This exclamation, comma, and that's the cut. This is the cut. All right? So it does x less than 3, comma, exclamation, bang, you know. And what about this next one? It's the same as before, but what? A cut here. Now, why would we want to cut here? Because we know that if it passes this one, it's not going to do what? Pass the third one. Do you see? I mean, we know that, right? So we'll put the cut here, this cut here, and this cut here, and now this one is, and now this second version does the same thing as the first version, but it's more efficient. And just to show you that it does, that it works the same way, let's just test it. So now, let's do, we'll just do. So let's do F2 of 1 comma y, 1 comma y, okay, and that should do what? Normal. Are you with me? And F2 of, just to make sure that it works on, we'll do 5 comma y, okay, and that's alert 1, and we'll do F2 of 7 comma y, all right, and that's alert 2, just like we expect. And this one that we did before that failed, it's still F2 of, now, you know, of 2 comma y, and then we try to match y. We want to know if we are in alert 1, okay, just to make it look pretty, okay. So, and we know this is going to fail. So, you know, we can't tell by just looking at this that it's different. But trust me, what the cuts did, I mean, if we were able to time this down to this number of CPU cycles, this one is more efficient because what it did is it cut out the stuff. So let's go back to our slides, you know, the unnecessary comparison. So, all right, so now watch this. This is a sequence. Now watch how this sequence works. This is the sequence of what happens. Now the only difference between this scenario and the previous scenario is what? We have the cut here and we have the cut here. And we demoed that it all works. But watch how the backtracking works this time. Now check this out. So first of all, we're going to assume that we do our same query, F2, 2 comma y, and then comma y match alert 1, right? So first thing we do x. So what happens here? X is what? How do you, what's the word I've always been using this. I haven't actually been explaining it, but instantiated. Remember that? Have you noticed that? So x is instantiated to 2, and then what happens here? Y is what? Instantiated to normal, and so that's a match, yeah, with x being 2 and y being normal. So therefore we go if, and so what happens now? It comes to here, right? Are you with me? So it goes to the right hand side, to this first goal. All right. Now, when it gets to this cut, because there's a cut here, right? When it gets to this cut, that commits us to this choice. It's like, you know those little spikes on the main lot out here that don't let you back up? You know those little things on the wheels that you can go one direction, but after you go, if you go in one direction, you know, you're going out of the parking lot. You go in one direction, but after you go in one direction, you can't do what? You can't backtrack. Oh, you say you know the way to do that? Anyway, well, yeah, right. Well, anyway, this commits us to this choice. So now here's another thing. When this cut execute, you have to understand, one of the primary attributes of cut is cuts always succeed. So remember that. Cuts always succeed. So because see, this succeeded, remember how we go from left to right in our goals? So x is less than 3 succeeds. Cut, oh, the cut, that also succeeds. So it's not like cuts fail. Cuts always succeed, all right? But what they do is they commit us to this choice. So then we come back up to here, are you with me? And we have succeeded, are you with me? But now what happens when we get to here? It's a fail because y was instantiated to what? Normal. So this is a fail. So watch this. Once this fails, what happens is, you see, once we got to this period, you know, on this, and we went back here, then everything that we would have done, coming all the way back to here and going to this and this and this, all of these are discarded. Now, do you see this visual? All of these possibilities now, because of this cut, are discarded, and it fails right now. There's no more backtracking. Now, is everybody clear on this? Yeah, question?
If there was another rule there, or what's the first part of the if statement called?
Oh, that's the head.
Okay, if there's another head.
Well, there can only be one head.
Okay.
There can only be one head of a rule.
Yeah, yeah. I mean later on, because there's two other rules, right?
Well, yeah, but each one of them only has one head.
Right. If there was a fourth rule
If there was a fourth rule,
with a different head, but it had the same if statement, would it give that as a possible answer still?
well, the only thing that it would never do that because we're doing F2. It's doing the F2. This first one is F2.
Okay.
If there's another F2, that's included in the ones that won't be considered.
Even if they have the same if statement that matches?
No, it's the head. Oh, I see what you're asking. No. It's not what's in the if statement, it's what's it, because what would normally happen, what happens is when you get to a cut and you try to backtrack through a cut, then all those possibilities are discarded.
Okay.
Now this has ramifications. It can get kind of tricky. But does everybody see how this visual works? All right? So here's the same visual in figure 5.2. Now that there's a cut here, all of these possibilities are discarded. Are you with me? This is the tree trace version. Is everybody clear on this? Okay? So now there is a very crucial and detailed meaning of the cut mechanism, and each one of these words, we're going to look at this in detail in the next few minutes. And let's just read it right now, for right now. Let us call the parent goal the goal that matched the head of the clause containing the cut. When the cut is encountered as a goal, now what did we say always happens with a cut? It does what? It succeeds. When the cut is encountered as a goal, it succeeds immediately. So when you think about going through a cut, that's like going over the spikes the right way. Are you with me? They don't stop you. Are you with me? So, but it commits the system to all choices made between the time the parent goal was invoked and the time the cut was encountered. All the remaining alternatives between the parent goal and the cut are discarded. Now, I'm going to walk you through a scenario where we examine each one of these words and we talk about the parent goal and all that kind of stuff, because it's a little, it can be a little complicated. There can be different complicated scenarios, but once you get the idea, I think you'll see.
So is the parent goal, is that the query that we type in? Is that what that corresponds to? What is the parent?
I'll tell you what. I'm going to show you an example of a parent goal with a visual on a later slide. So let's postpone that. All right. Now let's go back to our demo. Now now I want to explain the concept of a green cut. Do you agree that up here we had the original code, right? And here we have the same code but with the cuts. Yeah? So do you agree that if we were to remove this cut, if we were to take this cut and remove it and this cut and remove it, we demoed. The result is the what? The result is the same. If you can remove a cut and the result is the same, that is called a green cut. So there's no, Prolog doesn't know the difference between a green cut and a red cut. But that's how we label, that's a human label for the kind of cut it is. Do you see what I'm saying? So these are green cuts. But now look, you guys, we can make this even more efficient, because look, here's a third version. Look, why have this x is less than 3 here and then do what? Here we're comparing x with 3. What are we comparing x with here? Oh, we're comparing it with 3 here also. why have a comparison with 3 here and a comparison with 3 here? You know, that sounds like that's kind of inefficient. Are you with me? So look, so how about we use this logic? If x is less than 3, then we want y to be instantiated to normal, right? Okay. Otherwise, but now we're using the word otherwise. Otherwise is kind of like else. You see what I mean? Otherwise, if x is less than 6, then we want y to equal alert 1. Otherwise, we want y to equal alert 2. So we can actually do this logic with what we're going to call red cuts. Now, like I said, a cut is a cut as far as Prolog is concerned. It doesn't distinguish between them. But for our purposes of explaining the effects of the cuts, we label them as either green or red. And the definition of a red cut is, if you removed it, it would make a difference in the results. Okay, so we can't remove a red cut without changing the results. So here is our third version. Now watch this. We're going to do F3 x comma normal. So F3 is our third version. F3 x comma normal if what? If x is less than 3, and we do our what? And we do our cut, yeah? But now, what is our second one? F3 if what? F3x alert 1 if what? Just x is less than 6. Now, how come this is going to work? Because we already tested for less than 3, and we know that it's going to do what? It's going to, if it is less than 3, it's going to do what? It's going to cut, and we don't even have to test for, are you with me? And now what? Now can you see, now that you see seen the pattern, how are we going to do the next one? Actually, think about it. Yeah, why have an if? Good call. He said no if. Why have an if? Because why? The only way it's going to get to the third one is if what? Is if it failed the first one. Because if it succeeded the first one, it would be discarded. Are you with me? And is everybody clear on this? And so the only way it can get to the last is if what? It failed x less than 3 and failed x less than 6. So if we put x in there, that would be what kind of a variable that we don't like? That would be a singleton variable, and we don't like singleton variables. Is everybody clear on this? Okay? So this is why have the second test with 3? Why not just do it? And here we can demo the same, I mean, just to show you that it works, you know, we can do F3 and then say 1 comma y, okay? And see y is normal, and we do F3 and then 5 comma y, and that works. And we can do F3 7 comma y, okay, and that works. Are we good? Okay, so now let's take a look at the meaning of the cut mechanism.
Would it be comment whether your cuts are red or green?
Well, I have on this one, but normally it's you don't bother. I mean, but you know, it's not bad. It's not a bad idea. You hardly ever have too much documentation. So now let's see the meaning of this cut mechanism. Now here's the scenario. This is a great scenario. This book, I tell you, I've been through several Prolog books, and I really like this book by Bratko. And because this is the best explanation, this is a really good explanation of the cut mechanism. Now let's suppose that this is in our, look at what we have on the right-hand side here. Let's suppose that this is what's in our database. We have, this is the head, C, if, and these are goals, PQR, comma, cut, comma, STU, and then we have C, if, V, and then we have A, if, BCD. And what is our query? What's our query? See, our query is just what? A. So does everybody see that if our query is A, you know, here. If our query is A, what's going to happen? If our query is A, then what's going to happen? We're going to start up at the first one, right? This is not A. This is not A, right? This is C. So this is the, no match here, no match here. And now what's happening here? We get a match. So the first thing that we do is B. So that's shown over here on the left. That's A going down to B. Are you with me? And then the progression would be B, and let's say that B succeeds, and then C. But now, with this C, what's the possibility? We have to do what? Backtrack and go to this C followed by this C, right? So we would go to this C first, and so to satisfy this C, we'd go to this C, and what would happen? It would be PQR cut STU. So you see down here, it's PQR cut STU. Are you with me? But look, do you see that the arrow here on the cut is only what? One way. Are you with me? So here, so that means that if we ever get to this T, what can, you know, if we ever get to this T and this T fails, and then we backtrack to this S, and if this S fails, what happens? That's it. That's all she wrote. All right? Is everybody with me? So here, actually, before we go to the next slide. So can somebody tell me, how in the heck can we get to V? Yes, only if PQ and R fail. If PQ and R fail, then we didn't ever get to the cut and we didn't discard anything. Are you with me? So then we'll come back up here. So now watch this. So now here's the definitions. This is the clause containing the cut. All right? This is the clause containing the cut because there's the cut. Yeah. And this is the head of the clause containing the cut. Are you with me? So you know we have, this is the head of the rule. Okay? So this is the clause containing the cut. This is the head of the clause containing the cut. All right? And here, Chloe, here's the parent goal. Okay? So you see this C right here with the box around it is the parent goal. So what happens is we are in here and this is the parent goal. So that's what we mean by the parent goal. Are you with me on that? Okay, so this is the head of the clause, this is the clause containing, this is the head of the clause containing, and this is the parent goal. All right, and now what does it say? When the cut is encountered as a goal, it succeeds immediately. So do you see right here in this box? Now remember, C is the parent goal. But what is this box? What? It succeeds immediately. But it commits the system to all choices made between the time the parent goal was invoked, that's the parent goal, right, and the time the cut was encountered. So that's this time right here. So it commits them to these choices. Are you with me? This is kind of hard to parse through all of this stuff, but this is what it actually means. Okay, and then what does it say? All the remaining alternatives between the parent goal and the cut are discarded. Okay? So here C is the parent goal, and what it's saying is that all the remaining alternatives between the parent goal and the cut are discarded. So here's what's discarded. These are the ones that are discarded. Are you with me? Because C is the parent goal. And I've got this visual here that shows all this attempted backtracking, right? And so, but like we said before, if Q fails, the query can succeed through V. Actually, that's what Shane just said. If I remember when I asked, that's the only way that you can get to V. If Q fails, then you didn't do the cut. So if Q fails, the query can succeed through V. If T fails, the query cannot reach V. Now, so these slides are available for you. I think that's the last one. Yeah. Yeah, for this little go around. Okay? So that's a detailed description of how the cut mechanism works. And I think your next assignments, I mean, your assignments from now on, we'll do some stuff with cuts. All right? Good deal. See you next time.